Hey everyone, welcome back to MasterClass 11 and 12. Let's just cut right to the chase today. Before we can even think about conquering complex equations or balancing massive reactions, we absolutely have to understand the basic rules of the game. Just like physics has Newton's laws, physical chemistry rests entirely on 5 foundational pillars. We call these the laws of chemical combination. These laws literally govern every single chemical reaction you're going to study in class 11 and 12. So whether you're gearing up for your CBSE or your ISC board exams, mastering these concepts right now is going to make everything else down the line feel incredibly easy.
Here is our roadmap for today's explainer. 1. Conservation of mass. 2. Definite proportions. 3. Multiple proportions. 4. Reciprocal proportions. And finally, number 5, Gay-Lussac's law. Let's get into it.
All right, starting off strong with law number 1, the law of conservation of mass. Before we jump into the math, it's pretty interesting to look at the guy who basically started it all. Meet Antoine Lavoisier. Back in 1789, he was busy performing these incredibly careful combustion experiments. You have to realize, before Lavoisier, chemistry was honestly kind of messy, but he brought this strict exactness to his measurements. He proved that if you carefully weigh the reactants before a reaction and then weigh the products after, they match up perfectly. This obsession with exact measurement is essentially what birthed modern chemistry. So, here is your crisp, textbook-accurate definition. You might want to grab a quick screenshot of this for your notes. The law of conservation of mass states that during any physical or chemical change, the total mass of the products is always equal to the total mass of reactants. In super simple terms, matter is neither created nor destroyed. Whatever mass you start the reaction with, you absolutely must end with. Let's see how this actually works in a classic board exam-styled numerical. Step 1, we're heating up calcium carbonate. Step 2 tells us we are starting with exactly 5.0 grams of our reactant. Now, step 3, the reaction yields 2 products, 2.8 grams of calcium oxide and 2.2 grams of carbon dioxide. If we look at step 4, this brilliantly illustrates the law in action. When we add up those products, 2.8 plus 2.2, we get exactly 5.0 grams. The left-hand side perfectly equals the right-hand side. But wait, I need to warn you about a massive assertion-reason exam trap here. This law does have a limitation. In modern times, thanks to Einstein's famous E equals mc squared, we know that mass and energy are interconvertible. So in nuclear reactions, a tiny amount of mass is actually destroyed and converted into a massive amount of energy. Because of that, for nuclear reactions, this law doesn't perfectly hold up. Definitely keep that in your back pocket for exam day. Moving right along to law number 2, definite proportions. So now we're shifting our focus from the total mass to the specific composition of a compound. This is the law of definite proportions, originally given by the French chemist Joseph Proust. It states that a given compound, no matter what source it's obtained from, always contains exactly the same proportion of elements by weight. Basically, water is always H2O, combining hydrogen and oxygen in a 1:8 ratio by mass. And it genuinely doesn't matter if you scoop that water from a rainstorm, a river, or synthesize it yourself in a lab. Let's build your intuition on this by looking at Proust's actual experiment where he compared natural and synthetic cupric carbonate. The data here is wild. Proust took a natural sample, literally dug out of the earth, alongside a synthetic sample he whipped up in the lab. The natural sample had 51.35% copper, 9.74% carbon, and 38.91% oxygen. And the synthetic sample? It had those exact identical percentages. The source simply does not matter. The internal recipe of a compound is eternally fixed. Let's actually solve a high-yield numerical on this together. Imagine you're given 2 samples of common salt, sodium chloride. Sample 1 is already calculated for you at exactly 60.75% chlorine. Now, sample 2 tells you there are 3.888 grams of chlorine sitting in a 6.4 gram total sample. Let's just do the quick math in step 3. 3.888 divided by the total 6.4 multiplied by 100 gives us exactly 60.75%. The proportions are completely identical, which perfectly proves Proust's law. Okay, time for your second exam trap. The law of definite proportions totally breaks down if you introduce isotopes. Isotopes, as a quick refresher, are atoms of the same element but with different masses. For instance, carbon can be carbon-12 or carbon-14. If carbon-12 binds with oxygen to form CO2, your mass ratio is 12 to 32. But if carbon-14 forms CO2, that ratio shifts to 14 to 32. So the rule of thumb here is the law is only valid if the element is present in one specified isotopic form. That brings us to our third law, multiple proportions. This particular law was proposed back in 1803 by John Dalton, who you probably recognize as the legendary father of the atomic theory. Dalton had this realization that elements don't just combine in one single way. Sometimes the exact same two elements can combine in totally different ratios to form completely different compounds. Let's look at the formal statement. When two elements combine to form two or more compounds, the different masses of one element, which combine with a fixed mass of the other element, bear a simple whole number ratio with one another. I know that's a mouthful, but the absolute most crucial part here is that trick of fixing the mass of one element. By making one element a constant baseline, you can clearly see the simple whole number relationship of the second element. Let's break down a tricky percentage-based numerical that often trips students up on exams. Say we have an unknown element forming two different oxides. In step 1, oxide 1 is 50% element and 50% oxygen. That means 50 grams of oxygen for every 50 grams of the element. Now, if we fix the element's mass to 100 grams, that means we have 100 grams of oxygen. Simple enough. In step 2, oxide 2 is 40% element and 60% oxygen. If we fix the element to 100 grams again, we do 60 divided by 40 times 100, which gives us 150 grams of oxygen. Now, look at step 3. The oxygen ratio for our fixed element is 100 to 150. In step 4, that simplifies beautifully down to a 2 to 3 simple whole number ratio. See? Fixing the mass is the secret sauce. And once again, just like our previous law, the exam trap here is isotopes. Dalton's law of multiple proportions assumes that all atoms of a specific element weigh exactly the same. If you start mixing different isotopic forms of an element across these compounds, this beautiful, simple whole number ratio is going to completely fall apart.
All right, law number 4, reciprocal proportions. Okay, I need everyone paying maximum attention right now, especially my ISC students. This next law is an absolute heavy hitter in your specific curriculum, and honestly, it's notoriously abstract. This is the law of reciprocal proportions, proposed by Richter. I'm going to read this slowly because it's a lot. When two elements combine separately with a definite mass of a third element, then the ratio of their masses in which they do so is either the same or some whole number multiple of the ratio in which they combine with each other. Look, I know it sounds like a massive tongue twister. Let's visualize it so it actually makes sense. The best way to grasp this is using a triangle of hydrogen, sulfur, and oxygen. Imagine hydrogen and sulfur separately combining with our third element, oxygen. Hydrogen forms water, H2O, with a mass ratio of 2 to 16. Sulfur forms sulfur dioxide, SO2, with a mass ratio of 32 to 32. Now, let's fix the mass of oxygen to 32. To get 32 grams of oxygen in water, you'd need 4 grams of hydrogen. For SO2, it's 32 grams of sulfur. So the ratio of hydrogen to sulfur combining with our fixed oxygen is 4 to 32, which simplifies to 1 to 8. Now, what happens when hydrogen and sulfur combine directly with each other to form H2S? Their mass ratio is 2 to 32, which simplifies to 1 to 16. Finally, compare our two final ratios, 1 to 8 versus 1 to 16. They are simple multiples of each other. It's a perfect 2 to 1 relationship. Let's lock this in with a generic ABC percentage numerical just to be absolutely sure we've got it. Step 1, compound AB has 75% A and 25% B. Let's fix element A to 100 grams. That means we have 33.3 grams of B per 100 grams of A. Step 2. Compound AC is 42.86% A and 57.14% C. Again, for 100 grams of A, we do the math and get 133.3 grams of C. Step 3. The ratio of B to C combining with our fixed A is 33.3 to 133.3, which perfectly simplifies to a 1 to 4 ratio. Now for step 4. Elements B and C combine directly to form BC, which we are told is 11.11% B and 88.89% C. That's a direct ratio of 1 to 8. Finally, step 5, compare the two ratios. 1 to 4 divided by 1 to 8 gives us exactly 2 to 1, a simple whole number multiple. Honestly, it's just beautiful math. And finally, law number 5, Gay-Lussac's law. Now take a deep breath.
We are shifting gears entirely for our fifth and final law. We are moving completely away from measuring mass, and instead we're looking exclusively at gaseous volumes. This is Gay-Lussac's law of gaseous volumes. It states that when two or more gases react with one another, their volumes bear a simple whole number ratio with one another and to the volume of the products, assuming the products are also gases. But here is the massive board exam trap you cannot miss. This only works provided all volumes are measured under identical conditions of temperature and pressure. Gases expand and contract easily, so if the temperature changes during the reaction, the entire law fails. Let's look at the classic formation of ammonia gas as an example. Step 1 shows our balanced equation. N2 plus 3H2 yields 2NH3. In an experiment where temperature and pressure are kept totally constant, Step 2 shows that 2 liters of nitrogen gas perfectly reacts with exactly 6 liters of hydrogen gas. Step 3 tells us this yields 4 liters of ammonia gas. Let's look at Step 4. The volume ratio of reactants to products is 2 to 6 to 4. In Step 5, we simplify that, and we get this beautiful, simple whole number ratio of 1 to 3 to 2. Notice how perfectly these volumes map directly onto the stoichiometric coefficients of the balanced equation. It's incredibly satisfying. And there you have it. Those are the absolute rules of the game for physical chemistry. Now, to make sure you actually crush these concepts on exam day, you need to practice. Join our Telegram channel right now. The link is down in the description to grab the high-yield PDF notes, formula sheets, and handwritten numerical guides for this chapter. Also, definitely hit that subscribe button for MasterClass 11 and 12. If you hit a roadblock on any numerical while studying, just drop it in the comments below and we'll help you out. I want to leave you with a thought, though. If atoms combined in these perfect, predictable whole number ratios, how do we actually count something as invisibly small as an atom to do these calculations in the real world? Well, we are going to unlock that exact mystery in Part 2, when we cover the legendary mole concept and stoichiometry. Go ahead and click the Class 11 Chemistry playlist on your screen right now, and I'll see you in the next explainer.